Okay, we have finally made it here. Introduction to integration. I hope you're all excited. Okay, so just to motivate you and kind of summarize what we've been doing so far. So far, we've been studied something called differential calculus, which gives us information about the rate of change of a quantity and tells us information about the extrema of a function. Now, having a precise function given to us to provide us information about the total amount of some sort of quantity isn't always possible. It's typically a lot easier to get a certain amount of data that will give us more information about how a function would change with respect to time or with respect to something else. So if it's easier for us to find how something is changing, if we could do the reverse of differentiation, then we could figure out the function itself. And that's known, the reverse of differentiation, that's known as, anti-differentiation or finding the derivative. And this enters into a realm called integral calculus. Okay, so that's what we're going to be doing now. So differential calculus focuses on the rate of change of a quantity, and integral calculus tells us information about the total change over a specific interval. Okay, now to do the reverse of differentiation, anti-differentiation, we find something called an antiderivative. So an antiderivative, the definition of it is, if you have a function capital F prime, and if it equals to the f of x that we want, then the capital F of x is referred to as an antiderivative. So when you integrate by finding an antiderivative. And the connection between the antiderivative and the integral we'll talk about when we discuss the fundamental theorem of calculus. Okay, but for now, think about it more like the reverse of differentiation. So say, for example, we had little f of x is equal to 10. What would the antiderivative be? So before you differentiate and get an answer for 10, what would you have to have? Well, we could have, if we had, for example, 10 times x, and if I differentiated that, so f capital prime of x, that would just be equal to 10, and that would be equal to our little f of x. So it goes back to this definition here. If we had, say, 2x, for example, what function, if we differentiate it, gives us 2x? Well, it would be x squared. It's the reverse power rule. Okay, so, and then a mental check, if I were to take the derivative of this x squared, by power rule, I would get 2x, which is the same as little f, so I know that that's an antiderivative. So for polynomials, if you want to find the antiderivative, you do the reverse power rule. So instead of going, if we had xn, when we differentiate, we bring down the n, and we subtract 1. For finding the antiderivative, what we do is we go plus 1, and then we go 1 divided by the exponent. And we'll formally be defining this soon. Okay, but just trying to introduce you the notions, and then we'll introduce all the rules. Okay, so what type of examples would you get? So this is a simple example. Suppose that the population is growing at a rate given by little f of t is equal to e to the t, where t's time in years from some initial date. We want to find a function giving the population at time t. So what I'm going to say is let the population function be, I'm going to define it to be the capital F of t. Now, we're told is growing at a rate given by this. So if I want to find what the total population is given at a time, that corresponds to the antiderivative. So since our little f of t is equal to e to the t, what function, when I differentiate it, will give me e to the t? E to the t. Remember, the e to the power of t is the one that when you differentiate, if it's just this, it gives you the same thing back. And so because when I differentiate this, I still get e to the t, which is equal to little f of t, I know that that's the antiderivative. So a possible population function would just be f of t is equal to e to the t. Now, a natural question to ask ourselves is, hang on a second, is this the only possible population function? Because we know when we differentiate a constant, we end up getting 0. So, really, we could have had a population function like e to the t plus 1. If I differentiate this, I would get e to the t plus 0, which would be equal to my f of t. So that would actually work. Same thing with an e to the t, minus 7, or an e to the t plus 2 or 3. Plus or minus any constant would actually work. So this type of thing, when you have more than one function, specifically, you have some sort of function, but you don't know what the constant is, this is referred to as a family or a class of functions that would have the same derivative. So this means there is a family or a class, those terms are used interchangeably, of functions that would give the same derivative. They would have the derivative of e to the t. And so we have a theorem that tells us how to deal with this, or kind of what the rule is. So let's say we have capital F of x and capital G of x. And let's say that they're both antiderivatives of some function, little f of x, on a particular interval. Okay, then there is a constant c such that if you subtracted your two antiderivatives, the main part with x's, they would cancel out. So think about this. If I took this one, subtracted it from this one, the e to the t's would cancel, but I would be left with 1 minus 7 is 8. I would be left with a constant. So if I subtract any two derivatives, their difference is some constant. And this constant in integral calculus, this actually has a specific name. This is called the constant of integration. So what's the punchline? So antiderivatives, you can think about it almost as they're being unique up to a constant. Okay, that's another way to phrase this. Now, if we want to say, mathematically speaking, notation-wise, the family of all antiderivatives for a particular function, how do we write that down? And this is where this integration sign comes in. I'm sure you've seen it before. But if I want to say, okay, what is the family of all antiderivatives that correspond to f of x? And then we say dx, and I'll say what that means in a moment. We would say this is equal to whatever the antiderivative is, and then we always put plus c because it's true up until a constant. Now this expression, how do I digest this expression, the notation? So the symbol that kind of looks like this weird sort of S, this is the integral sign or the integral symbol. So this is the integral sign / integral symbol. Okay, and the f of x part, so the thing that's after the integral sign, we refer to that as the integrand, where the entire thing is called the integral. Now, what is this little dx thing right here? And actually I'll write this here. So integral f of x dx is called the integral. The entire thing is called the integral of f of x, where the dx tells us what we're integrating with respect to. It tells us our variable. It tells us that we're integrating with respect to x. So the integral of f with respect to x is how we sort of phrase that. So I'm actually going to get rid of this. In English, we would phrase this as the integral of f with respect to x. Okay, and so that's how we say that in English, this notation here. Okay, and this tells us what our variable is. Okay. This integral in particular, it also has another specific name. It's called an indefinite integral. We're going to formally define these next week. Indefinite integral. And it's because there's no bounds. So by bounds, we'll talk about in a second, but sometimes you can have integrals with numbers here. So you could have like an integral with, say, like 1, 2. When you have numbers there, they're called bounds, and we would call them definite integrals. But when you don't have bounds, the name of this type of integral right here, this is called an indefinite integral. Once we talk about the other kind, we will formally kind of introduce these again or formally define them, but just starting to give you some of the buzzwords now. Now, okay, this is all very nice. That's great. We know how to say it in English. We know how to write it in math. Where exactly does this notation come from? What do integrals mean? We know on a function, if I'm talking about the derivative, right, at a certain point, I'm looking at the slope of a tangent line, okay? But, you know, what do we think of drawing-wise on a graph when we're talking about an integral? So we're going to go through and derive that right now, okay? So say you have some function f of x, okay? And say I'm only interested in between the interval ab. Okay, sometimes we're curious in the entire domain, but say there's a specific region I'm curious about. It'll be easier to explain it. Finding the integral, or integrating within this region here, corresponds to finding the area under this curve. So derivatives correspond to tangent lines. Integrals correspond to areas under the curve. Okay, that's what they mean. Okay, so that's nice, but how the heck do we still come up with this formulation? So a way we could approximate the area. So we're going to basically derive how we get the integral expression. So how do we come up with this? So a way we could approximate the area in this region here is I could be very crude and I could, you know, draw a few rectangles. You know, I could draw a rectangle here. I could draw another rectangle here. And maybe I draw another rectangle here. So then I know how to find the area of a rectangle. That's just length times width. So I could find the area of this, add it to the area of this, add it to the area of this, and that's good. But that's not going to be the best thing, because even as you saw when I drew it, you know, if I drew it like this, I'm over approximating. So instead of using 3 rectangles, let's use a few more of them. Let's use, say, n many. So what we do is we split up this region between A and B of rectangles of the same width. Okay, so I'm going to have a rectangle that's here, a rectangle that's here, one that's here, one that's here, and I'm going to keep going, and I'm going to do n many of these. Okay, so this will be the last one. So I'm thinking about this, so I have A to B, so sometimes A, we call it x naught. Okay, so the starting point. But this rectangle here, this is going to be the rectangle at x1. This is going to be a point x2, x3, x4, dot, 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 xn minus 1, and then the xn would correspond to b. And as I said, the width of these things, the width of these rectangles are all the same. And it's a tiny width. So tiny width, mathematically, we can write that as delta x. Now, so that's the width of these rectangles. What about the height? Now, depending how I draw my line at the top, I'm going to over approximate or under approximate the area. So what do I mean by that? So say on the right side, if I draw my point there and then draw the top of my rectangle like this, you know, point there, draw it across like this, point there, draw it across, point here, draw it across. I'm over approximating, right? Because I'm above this blue line. So this is overestimating the area. If I instead, maybe what I'll do is I'll draw the top, I'll put my point on the left side, and then I'll draw like this. Then I'll draw like this, like this, like this, so on and so forth. Well, then I'm missing out on all these parts. So in calculus, when we're doing something like this, we have different ways to approximate the area of a rectangle. The math students go through this much more formally. Left-handed points, right-handed points is what they're saying. Another thing that you could do, which is a much better approximation, is you can draw the point in the middle. So then overestimating and underestimating, you average it. But we're not going to focus on that in this class. But the concept is that the way you draw the top, it will make a difference about the approximation. That's what I want you to get out of that. But regardless, the top part, So if we draw across like this, say we have the orange line here. Okay, so we'll do it putting the point from the right. This top corresponds to this y value. How would I find that? Well, I would plug in, say, x1 into here. The top of this one would correspond to when I plug in the second point, so on and so forth. Okay, so that corresponds to the height of these rectangles. So the area of one of these, okay, let's say this first one here. Okay, so the area of that rectangle is going to be length times width. Okay, my width is my delta x, and my height corresponds to f of the x1. Okay, where the x1 just means that I'm at my first rectangle. X1 means right point at first rectangle. Okay, so if I want to find the area under this curve, what do I have to do? I have to take this area, so say like A1 plus A2 plus A3 all the way to plus AN. So this is going to be A1 plus A2 plus all the way to AN, where each of these A's, their length and their width, the first one, which I wrote down, was f of x1 times the width, which is delta x. And then the next one, the height would be f at x2, delta x. And then it's true for all n of these. Now, notation-wise, I don't know if you saw this in high school, but you should have. When you want to plus like this, add up, there's a special symbol that means add a whole bunch of terms up that look very similar. It's the summation sign. So I could rewrite this. You don't have to do it this way, but I can rewrite this in sum notation. I going 1 from n, f of xi, delta x. Again, don't worry about this notation. You're not going to be tested on it, but just to show you kind of where this is coming from. But this is still just a crude approximation, right? If I double the amount of rectangles I have, this area, when I add them up, will be more precise. If I triple them, it'll be better. If I quadruple them, even better. So if I think about, you know, in the limit as n goes to infinity, infinitely many triangles, I would be able to get my area exactly. So in the limit, if we consider the number of triangles as n goes to infinity, we'll finally end up getting better approximation, and eventually we'll get there. So if I think about taking these, the limit as n goes to infinity of the sum of all of these triangles, all n of my triangles here, that would give me my area. This expression right here, this one right here, in calculus, this is known as the Riemann sum. Again, you're not going to be tested on this part. Known as Riemann sum. But it's really important to know this because if you read about it anywhere else, I want you to know what they're referring to. And why is this so important in calculus? Because in calculus, this thing right here, the limit as n goes to infinity of the sum, okay, Riemann sum, that is what the integral sign, the integral symbol represents. So this expression for a here, a equals the part in purple, that turns into an integral. And then this f of x, we get rid of the I there because it's kind of tied into this. And this small change in x, this is the thing that then turns into the dx. Okay, it tells us what we're integrating with respect to. Now for our particular picture, we didn't do this across the entire domain. We could have, in which case we would just have this. But we did it in between two particular points. Okay, we did it in between the points A and B, where this is the smaller point, this is the larger point. When I was talking about bounds before, this is what I meant. So these things are called bounds. We're integrating between a specific region for our variable. Okay? So that's what's referred to as a definite integral. When there's no bounds, It's indefinite. And again, we will review this next week and give a formal definition. Okay, so this is known as a definite integral since it has bounds. How you treat integrals with and without bounds is slightly differently, but we need the fundamental theorem of calculus to figure that out, which we'll talk about later. And it has to relate to that constant of integration. But again, don't worry about that for now. The thing I want you to take away from this introduction is what? That integrals represent the area under a curve. Okay, derivatives represent the slope of a tangent line. Integrals tell you about a total quantity. Derivatives tell you about the rate of change of a quantity. In English, we say this as the integral of f with respect to x. And this tells us that I'm not differentiating, I'm doing the reverse, I'm integrating. And integrating, so far we only looked at e to the t and a couple of numbers here, but if I give you something and I tell you to find the antiderivative, try to think about a function that if you differentiate, this is its answer. Okay, so those are the main things I want you to take away. Read through this, try to absorb it. I know that this is new, but hopefully that's an okay sort of introduction, and then we'll just keep going next week with this. Okay, thank you very much.